My name is Michael,
And I'm John.
and we are both auditing engineers at Quantstamp, a Web3 security firm. So today we're going to go through a little more of a technical talk, and we're going to lead you through some easy-to-miss Solidity bugs. First of all, obviously security is super important. I think as some of you guys saw from the last presentation, we've gone through some of the security concepts of how to develop things from a high level. We want to dive into some very specific Solidity bugs that we can look at from actually real-world audits. So everything that we go through today is actually going to be from an audit that we have done, and then we have simplified the bugs and tried to boil them down into a couple slides that we can share with you guys. Obviously, in any security sense, in the Web3 space especially, we have lots of money at stake, reputation at stake, and so it's essential to avoid bugs at all stages of the process in order to prevent losses and prevent reputation damage. So yeah, the goal of this presentation is 100% to get people aware of bugs that are lesser known, but still very common and very easy to miss in our security reviews.
Yeah, so before we talk about easy to miss Solidity bugs, just to give a little background here, like we consider some bugs to be easy to find. And these are bugs that usually you cover in the beginning of your smart contract career. As soon as you begin an auditor, one of the first things you'll do is open Zeppelin's Ethernaut exercises, which cover a lot of these easy to find bugs we have mentioned here, like reentry risks, proxy misimplementations, on-chain privacy issues, signature replay, etc. Those things are pretty well known and standard. They've been around for a while, so these bugs are well known and shouldn't really be leading to hacks in new products. Additionally, we consider easy to find bugs anything that can be detected by a static analysis tool such as Slither. So this category of bugs are bugs that we consider easy to miss. So during the line-by-line manual audit process of a security audit, these are bugs that maybe at first glance they appear correct, the logic looks correct, the logic looks sound. However, due to nuances either in the Solidity language or the EVM or networks themselves, this can lead to significant issues down the line.
All right, so the first issue that we're going to dive into is opcode functionality on various EVM networks. A lot of developers, especially first-time developers, are going to look at the EVM and Solidity, and they're going to dive right in, developing based off of the current state of the Ethereum mainnet. And unfortunately, with how everything is going right now with L2s, not every network is 100% EVM compatible. And so there are opcodes and lines of codes that will work in one way on one chain and another way on a different chain. And so you have to be completely aware of this kind of situation. So a good example here is the self-destruct function. This is actually being deprecated, so I wouldn't really recommend using it anywhere. But on Ethereum mainnet, it will no longer destroy your contract. It will just return all of the ether to you. However, on an L2, this might actually do nothing. The opcode will be dead and just revert. And so if you were expecting to be able to withdraw all of the ether from your contract using self-destruct on an L2 and you had it audited and say didn't tell the auditors that you were expecting to deploy it elsewhere, you could run into a situation with locked funds. So there's a few different solutions for how you could go about avoiding this problem. One that we have displayed here is using the chain ID as an indicator to show how you want to operate on different EVM chains. So for example, if the blockchain ID is 1, you're on Ethereum mainnet, you may want to just call self-destruct and get your ether back, even if it doesn't destroy the contract. Maybe on an L2 instead, with a different block ID number, you want to call transfer to move your funds out of it. Another way you can do it is to have different versions of your project for different chains. I think this complicates the process a little bit more. And then finally is kind of a allusion to one of our papers that we've done recently actually was about a pre-compiler step where you would pre-process your Solidity to produce a gas-efficient version of it for each chain depending on different opcodes that might exist there.
Yeah, so this bug is really interesting and kind of inspired this talk. This contract is a very simple staking contract where the user can deposit funds. However, the issue is very subtle here in the fact that the starting stake variable is declared in the memory space of the smart contract, and the total staked, which is actually the smart contract storage itself, never gets updated in this line here that we're pointing to. So as an auditor, just really be careful about local variables and where they're existing in the smart contract storage. And as a dev, please double check that the contract storage itself is actually being updated. And this is quite easy to miss because it seems like you're taking the user's message.value, updating it to starting stake, but this total staked variable in the contract state itself never actually gets updated. So the fix here is pretty straightforward. You would usually only use a local variable for intermediary operations like we see here, calculating the net user stake. And then the contract state needs to be directly updated itself. So after the stake does take place, the total staked would be reflected in the contract state.
All right, another instance that is kind of the inverse of this one is using storage variables in a function when you shouldn't. So in this instance, we have a staking contract, and we're going to say that we have a struct, which is used to determine how much ether needs to be withdrawn from the contract. In this bottom function here, we have the process unstake, where we're going to take the unstake request and store it in a variable within the function. And the bug here is that we use storage instead of memory to store that struct. So when we grab the request, we're storing it. We're not actually storing it in a memory variable in the function. We're just having a pointer that looks at the storage in the contract. So on the next line, when we delete the storage request, we are actually going to get to this third line where we're supposed to send the funds, and it's going to be completely zeroed out. So you have to be very careful about where you choose to store things in your contract. So the obvious solution, which may be a bad fix, would be to let's just reorder the lines. If we delete the unstaked request after we withdraw, then it should be fine, right? Well, this actually introduces one of our easy-to-find, well-known bugs, which is a checks effects interaction violation, which introduces a reentrancy bug. So you would need something with this, like a reentrancy guard, to actually prevent this from causing lost funds. A good solution to this would be to just store the request in a memory variable. So now instead of just pointing to where the values are in storage that we want to withdraw, we're now creating a copy of the values, putting it in the stack, and then we can use that value even after it's been deleted from storage to withdraw the ether.
Awesome. So this bug involves incomplete struct initialization, and we see this come up in our audits oftentimes in complex contracts that need to define something like a configuration struct that has many different fields. So in this contract, we have another staking contract, and in the constructor, the intent of the developer here is clearly to initialize all fields of the stake config to these default values. However, it's a little easy to detect that the stake boost wasn't assigned in the stake. And did I say easy? It's hard to see that. Sometimes, right, you can't see that if there's a lot of different fields. So what ends up happening is stake boost is going to default to that 0 value. And as soon as the user stakes, they're actually zeroed out the funds that they've sent in, which is clearly no good for anybody trying to use your product. So a good fix here, there's two fixes, right? So instead of assigning using dot notation for the struct itself, you can lean on the compiler's safety guarantees by using the struct constructor syntax. So the Solidity compiler itself will actually throw an error if you are missing a field in your constructor syntax that isn't detected if you were to use dot notation to initialize the fields in your struct. So this would be the preferred fix because you do get those security guarantees from the compiler. But if you insist or you prefer to use dot notation to assign the fields of your struct, a good practice is to compartmentalize your logic into different functions, such as something called a init config, so that devs during code reviews in the development process, you can look here and make sure that the struct is actually initialized properly. And during the audit, auditors would be able to look there and guarantee that the struct was indeed initialized correctly.
All right, so this one plays off of the struct initialization error in a similar manner by looking at how EVM handles default values. So in this case, we have a pool launching contract. We have a pool status state variable, and it's going to hold an enum of type pool status. So in this version, we have launched, paused, and closed are the three states of the pool the developer expects the pool to ever be in. And then we might also have like a pre-launch phase that we expect users can't interact with the pool yet, but we say that it's not launched yet, so we don't represent it in the enum because they don't think they need to. But since the status was defined as a state variable and then not set during the constructor, it is actually going to default to the first value in the enum always. And so that would mean that right off the bat, as soon as this contract is deployed, the deposit function would be allowed because the pool state would be in the launched phase. This may not be intended, and it can happen in a lot of other different circumstances too, where anytime there's an enum and the default value is the first one, if that's not an okay or safe state to be in, then we need to evaluate adding a new one on top of that. So our fix here would be to add a pending state as the first state in the enum. This would make it so that it defaults to the pending state and then needs to be manually changed to one of the launched, paused, or closed states later.
Great. So I like this issue because there is no issue, and the compiler actually allows this to happen. But there are some things that can really go wrong here. In this contract, we have a parent contract deposit and a child contract deposit with access control. And I'm sure we can see that both of them are incorrectly declaring a private variable account manager. But because these variables are declared as private, there's actually no collision of this storage, as one account manager lives solely within the deposit contract and another lives solely within this child contract deposit with access control. So we can see that only the child contract allows the account manager to be assigned, and it's only going to assign to the state variable within it itself, and this will not be reflected in the parent contract. So when the inherited function get account manager does get invoked on the child contract, it's actually going to read stale data from the parent contract, which would likely just be an undefined zero address value here. So this isn't an issue, again, in the compiler, but it can lead to issues down the line, as we saw in client code. And quite frankly, the issue with the code that we were auditing here was that deposit, this parent contract, was never meant to be deployed as a standalone contract on its own. So the devs should have just declared it as abstract to be only inherited, and then we could just isolate the storage only into that abstract contract, so there's only one account manager ever being referenced throughout the system.
All right. So this is one of the more complicated ones that we have here. This contract is, well, it's actually two separate contracts, parts of a bridge. So in the top part, we have the origin chain where you'd be sending tokens from one chain to another, and the bottom you'd have the destination chain. The issue here is that on the origin chain, we are allowing users to specify a payload, which would allow for arbitrary calls on the destination chain. So you might have some, say you want to bridge USDC from mainnet to, say, Zircuit L2. You might have something that happens on Zircuit that you want some action to take place when the funds actually arrive there. And so we want them to be able to specify what actions they would like to take. But the problem here is that this is just a little too free from the user's standpoint. So the risk here is that we have stalled transactions, lost transactions. When you're focusing on something that's going from one chain to another, you lose the atomic guarantees of operating within a single chain. And so now we need to focus on problems that could occur if, say, one transaction doesn't execute on the second chain. Can it be replayed? If it gets to the second chain and fails, can it be retried, or is it going to fail every time? Is the user paying enough gas on the starting chain to pay for the operation on the second chain? And when you give all these options, such as an empty payload that the user can specify anything, we're very likely to run into issues. So as I've kind of been alluding to, the auditing tips is anytime you have generic bytes as user input, we're probably doing something wrong unless we're working with like a wallet. We want to confirm that our cross-chain execution is in somewhat of a box state so that we can limit the number of operations that the user can actually perform. And we want to remember that different EVM chains, again, operate a little bit differently. So just because it sounds like good opcodes on the origin chain doesn't mean it's actually going to work on the destination chain. So once again, we want to sanitize inputs. We want to restrict and give options for what the user can do instead of allowing for arbitrary execution. We want to enforce maximum payload sizes so that we don't run into issues where, actually I should go back. So we have a try-catch block on the destination chain. And this would theoretically handle any errors that we would run into, but, sorry, we activated Siri. This would theoretically handle any errors that we would run into, but the one it can't catch is if you run out of gas on the destination chain, it's just going to fail and the whole bridging operation won't work. So we need a way to work around that and limit operations that are going to run out of gas on the destination chain.
Awesome. So those were our main category of like our easy to miss Solidity bugs, but we have some honorable mentions out there. So any contracts that support multiple tokens, please do not assume that all decimals of those tokens will be the same. So perhaps read the contract state for the decimals when normalizing values. Any NFT marketplaces, please keep your eye out if it's planning on supporting the CryptoPunks contract. The CryptoPunks contract has been around before many of these token standards became the norm, so it operates in a very unique fashion. Additionally, if there's any staking contracts and needs to be accounting between user stake funds and the reward tokens that are given. So if USDC can be staked and rewarded out, there needs to be an accounting separation between the user's funds that were deposited and the rewards that are to be paid out, often provided by the team, which sort of relates to like the risk of just reading the balance of the contract. And then another thing that we've seen is if usually this is in the earlier stage of a protocol, but if there's any manual price updates that are to be given by the team, maybe it's like a ratio of rewards or something like that, that is almost always going to open up the contract to the risk of front running and back running for optimal gains and maximum extracted value. So with those, before anything like withdraw for a certain calculated reward, if that can be reassigned by the team, perhaps prefer an update on those operations instead of waiting for perhaps like a price update once a day. Yep. So in conclusion, even our easy to miss bugs can lead to severe consequences. Lean on both static analysis, in-depth audits, manual line review, any automatic tooling during the audit process itself. Then just generally embrace best practices for Solidity smart contracts, such as proper state updates, full initialization. Do not rely on default values. It's even safer to assign the default values explicitly than to just assume that they're going to work there. And always, always sanitize the data, especially if it's user provided. So stay proactive. Always read up on crypto Twitter, security best practices, recent hacks, and stay safe out there.
Awesome. Thank you, guys.
We'll be around to chat after.
We have about a minute and a half if we have time for questions. I don't know. Might be close. Any questions?
Thank you.
Looks like we got one. Oh, can we get him a mic? He was raising his hand.
Oh, yeah.
Oh.
We don't have much time.
Thanks. Yep. So does Quantstamp do security audits for other chains besides EVM chains?
Yes, definitely. We've done audits for all EVM chains, Solana. We've done stuff for Sui. We've done stuff for Ton. Yeah, we've done Cardano. We've done just about everything, including the kind of Web 2 node side of things as well.
Is there any talk about using AI to automate some of these audits that you guys do manually?
We do not have a talk on it, but we do, if you want to come talk to us later, we do have some insights on that.
Also, maybe let's talk after. Let's talk after down there. Thank you guys again.
Thank you.